Hey, welcome back to Fat Mama Physics. In this video, we are on to section 2 of the Exponent unit, unit 2. And in this section, we are going to look at powers of 10 and the zero exponent. So I will actually, in this particular lesson set, there is some examples where I talk about the zero exponent and also what the power of, with the base of power, a power of base 10 and what that looks like, the utility of it, and eventually I kind of want to show you a few kind of a scientific notation things, and which may even clear up a few doubts or a few questions you have about your calculator, especially when you have that times 10 to the power of something on the side of your calculator. I will hopefully be able to clarify some of that in this lesson. So, yes, I did say that every lesson I will start off with a board game to kind of showcase what this lesson may be about. The one thing I think would be cool to take away, aside from using the numbers with powers of 10, is the idea where if you have a zero exponent, it doesn't matter how large your number is, or how negative your number is, or whatever it is, you're always going to get 1, okay? And that's kind of what I want to showcase with this game. And the funny thing is, the theme applies to pretty much every game in itself. But let's turn over to my other camera. Hopefully I'll keep this short. Alright, so this game is called Santorini. It looks like this. Okay, let's just take it off. Ooh, it actually looks, it's a nice, cute little game. It's a 2-player game, so 1v1. And it's looks like you're trying to build things. So there's a platform, and these you're building these things that look like those little that place in Greece. I totally forgot the name of that. But anyways, it's looks like a nice tourist location. So here you go. Notice that this thing that you're building has actually 4 levels with the top included. So that's kind of what you're doing. But here's here's how you win. Okay? You win by having one of your guys, either this guy or this guy, at the top of this tower. So the first person to reach that wins. Or if the other team has no legible moves, then you also win. So, usually, so this is kind of the gameplay. So notice that every person gets 2 of these builder dudes, okay? So, once the game begins, then what happens is your person has to move at least once, and the person can move orthogonally or diagonally. So that person moves 1 step and then performs a build action. It has to be the same person. So let's say I move forward once and I build this guy over here. Okay. Now this guy, when he the opponent does something. When this guy moves, he may move up 1 level. He can never jump 2 levels, but he can move 1 level up or 1 level down. So he continues to move and maybe continues to build. And hopefully I just build around myself and maybe away from my opponent. Maybe there's some cases where I want to just prevent them from doing stuff. But anyways, these are that's kind of the gameplay. So once we just keep building, and hopefully at one point we'll have 1 person here at the top. Or if the other team cannot move and build, then that's also when they lose and when you win. So it comes down to the point, it's like it's a different variant. It feels like chess. There's strategy, there's ways to prevent the other team from doing what they want to do. Oh, and that's what this little thing is for. So whenever, say I have this building here in the middle, and then I'm pretty much about to get to the very top level, then what that team can do is that other team can move his character right beside my right beside this building and build this, build that to cap it off. And that prevents anyone from getting to the top. And yes, you can build from any level, and you don't have to just build on your building. You can build other people's buildings too. So that's that. So there's many ways to strategies to stop your opponent from doing what they want to do. Which makes this game interesting, of course, which makes it a game. Okay, so that's it. And then the reason why, how I thought it would relate it to just, I mean, it doesn't have to be this game, it could be any game, but the idea how no matter how many people are playing in a game, there's always going to be that one winner. So it's almost as if you're taking something to the power of 0. No matter what you're taking to the power of 0, you're always going to get 1. So you're always going to get winner in this game. And based off the mechanics of this game, there's no way for there to be a tie. So that's the other reason why I picked this game, because you can't tie in this game. The turn you reach the top, or the turn you can't make a legal move, then the game is over. Okay, and the winner is declared. So there you go. That is Santorini. Thank you for listening, and back to our lesson. Okay, so let's take a look at what we have here. So let's see how fast I go, and depending on how fast I go, I may be able to cap this off at 1 lesson per page. So we'll see. Okay. Oh boy, look at this. So, why is it that something to the power of 0 is going to be 1? So, what that means is, even if I have something that's 10, I don't know, 9, 9, 9, 9, 9, 9, 9, 9, and no, I don't speak German. And if I raise that to power of 0, that's still going to be 1. If I take some decimal, doesn't matter what it is, or actually if I take a very small decimal, even that, I can keep going, all to the power of 0, that's still going to give me 1. And it doesn't matter this is negative, that is negative, blah, 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 blah. Whatever that case is, everything is going to be 1, 1, 1, 1, 1, 1. Oh, wait a second. This one, haha, B and C. Actually, no, wait, only B, because this is, that will be 1. So notice this thing that is not in brackets, the 4 that's not in brackets, I still have 4 to the power of 0, which is 1. But remember that negative in front means I have to multiply the whole thing by -1, which makes this -1. Okay? Everything else is just 1. So, very convenient sometimes, and also reduces a lot of work. Oh yes, did you know that even if I take any variable to the power of 0, that is still going to be 1. Even if I don't know what that number is, it's still going to be 1. So that's pretty cool. Now, why is it that anything raised to the power of 0 is 1? Well, think of it this way. We don't actually have to use base 10. So let's use any base that we want, including base, I guess 10 is the easiest. Okay, fine, I'll use 10. So if I have to write this out, this is 1,000, okay? This is 100, and this is, of course, it's just 10. Notice if I go up a power, I am multiplying by the base again. So I get another multiplied by 10, another multiplied by 10, and that's as if I go up. Now, if we go back down the opposite direction, so going down, then I am effectively dividing by 10 every time. So that means I have 10 to the power 3. Let's say I take this, I divide it by 10. That's going to give me the one power that is lower, which gets rid of 110, as you can see. And if I divide this by 10 again, that is going to give me 10. If I divide this by 10, oh, we keep on going. Then 10 divided by 10 gives us 1. And that's 10 to the power of 0. Because if we go the other way, the pattern flips. The pattern becomes divided by 10. If instead of multiplying by the base again, we divide by the base. And 0 just means that I take my base and I divide it by itself, and anything divided by itself is going to give me 1, okay? You're wondering, ooh, then what happens if this pattern continues? It's not part of our curriculum. You're not required to know this on the test or a quiz, but for your interest, imagine I have 10 to the power -1, and this pattern just keeps going. And yes, it actually does. You're not required to learn negative exponents, but here, notice there are negative exponents now. And based off of our pattern, which is divided by 10 every time, let's divide 1 by 10. We're going to get 1 over 10. As a decimal, this is 0.1. And then let's divide it by 10 again. This is going to be, oh, I'm running out of space. Ugh. Let's use this green pen here. This is going to be 1 over 100. This is going to be 0.01. And then the last one is going to be 1 over 1,000. That's going to be 0.001. So that's interesting as we go into the negative exponent is instead of multiplying the base by itself, it becomes dividing by the base. Dividing by one base at a time. So that's really that's pretty interesting. Although the only one that you are required to know is this one here. That anything to the power of 0 will always equal to 1. Okay? So there you go. That's the 0 exponent. That's it. It's that easy. So let's talk about 10 powers with base of 10 instead. Notice that my previous example with the power of 0, I could have used any base. I just chose 10 because it was more, 10 is usually easier for us to visualize. So that's that. Okay, here you go. Example 3, write the following numbers using powers of 10. So example 3 is pretty much 3 and 4 are questions that get you to think about the different, to think about place value, essentially, is what it is. And representing place value as an exponent, or as a power, essentially. I'm going to show what that means. Does it have a lot of functionality in real life? Not so much. It's really for you and building understanding. So I'm going to try to fly through this a little bit. What I really want to get at into the next lesson is scientific notation, which actually has functionality. And you will use it, you will see it, and you will use it in science, in senior science classes. And since I teach that, I definitely have to advocate for this. So let's just quickly get through 3 and 4, for especially those of us who need a refresher on place value. The first example is done for us, 3a. So we want to write 3,452 using powers of 10. So the first thing that we should do is to identify the thousands place value, the hundreds, the tens, and the ones. So we know that 3,000 here is is made up of 3,450 and 2. So we're kind of splitting up the place values that way. And if we split it that way, since we can write the top as an addition statement to get 3,452, then whatever we break this down into, we can also write that as an addition statement. So if I take this 3,000 and break and say, this is just 3 times 1,000. This is equal to 3,000. I can do that for the 400, do that with a 50, and with a 2. So 4 times 100, 5 times 10, 2 times 1 gives us all of the top numbers. Now, that's elementary math. Since we are learning about powers, we can represent these tens and hundreds and whatnot as a power with base 10. So with 1,000, that's 10 to the power 3, and 10 to the power 2, 10 to the power 1, and since we just learned that anything to the power 0 is 1, that's 10 to the power of 0, which gives us 2, ultimately. So we finally get this as our addition statement for the top value. And that's essentially what you want to do for each of these examples. For number 3, I'm going to do the first one and give you a chance to try the subsequent ones down below. So this is 43,219 can be broken up into 4 times 10,000, okay? And this is plus 3 times 1,000 plus 2 times 100 plus 1 times 10 plus 9 times 1, basically, okay? So if I want to convert all of the powers of 10s into an exponents or into powers, this is what it will look like. I still get 4 times 10 to the power of this many. And hint, if you take a look, what's the relationship between the number of zeros and the exponent in each of these base 10s? Yes, if the number of the exponent tells you the number of zeros there are. So, hey, this would just be 10 to the power of 1, 2, 3, 4. Okay? Plus 3 times how many zeros? 1, 2, 3 zeros. Okay? Plus 2 times how many zeros? 2 zeros for 100. Okay? And then 10 is just 1 0. Okay? And then 9 times 10 to the power of 0 because there are no zeros. Haha, there we go. So that's example B. Guess what? Why don't you try C and D? Good time to pause the video. Okay, so here we go. Alrighty, so let's do this one. Notice that there's a bunch of nothings in between all these different place values. So that just becomes 6 times 10 to the power of 1, 2, 3, 4, 5, 6, 7. That's 7 zeros. 1, 2, 3, 4, 5, 6, 7. And how do you know that it's 7 zeros? Think about, oopsies. If I had a decimal place right after the 0 here, how many times would I have to move it to get all the way to the 6? 1, 2, 3, 4, 5, 6, 7, 8. Oh, did I miscount? Ha ha ha, I miscounted. So there should be an extra 0. So again, counting the number of zeros all the way until the decimal reaches the 1 place value before that number. So number 6. Next up, we have the 5, and that's it. The 5 is going to multiply. How many does it move over? The decimal place. 1, 2, 3, 4. So 1 and 4 zeros. So pretty much that gives us 6 times 10 to the power of 8 for 8 zeros, okay? Plus 5 times 10 to the power of 4 zeros. Okay, there you go. And 3 billion. Okay, that's easy because there we go. We can just write billion as, well, if you want to write with all the zeros, we can do that. So that's going to be, this makes it 1,000, this makes it 1,000,000, and this makes it 1,000,000,000, okay? And I don't have to have the brackets. But then converting this to 10 to the power of something, this just becomes 9 zeros. So there you go. Now 3 times 10 to the power 9 looks more like scientific notation, which we'll talk about in the next lesson. So here we go. Let's write the following here in standard form. Standard form, it just means expanding everything out and just writing it as the actual number. So for example, this one here is just going to be 1 and 4 zeros, just like the number itself. And so pretty much the opposite of example 3. I don't know why this keeps happening. So going back here, so that would just be 5. And really, if I don't have any another number, this would just be 6 zeros since I have 10 to the power 6. Okay, and last but not least, this one that looks a little bit more convoluted here. So if you want to, you can write this out just for visualization. This is 3,000, okay, plus 600, plus this is 10 to the power 0. This is just equal to 1, so that's just 5. So that's 3,605. There you go. Okay, so that was a pretty long lesson. But that's it. I am going to conclude my lesson there, and scientific notation will be the next one. So I thank you for watching. Good luck, Fat Mama Physics, signing out.